Howdy there, folks. Switching up my greeting. Okay, I got a very helpful hint that apparently the camera has not been getting the top, and I've been writing all the best information right up here so you guys can see it. Well, maybe I'm exaggerating, maybe, but in any case, I've made it a little bit farther back. We'll see how this goes. That kind of stuff is super helpful. So if you guys see stuff like that, let me know. Okay, so sort of moving on with stoichiometry and playing around with molar masses and stuff like that. We're going to look at, we looked at how if you have the formula of a compound that you can figure out the percent composition. Okay? Well, it turns out you can go the opposite direction. What if you have, you know, the percents of the mass percents of the various elements in your compound? Can you figure out what the empirical formula is? Okay, and as it happens, you can. And this is these kinds of things are not just, you know, oh, what a fun exercise in math. Let's do this. There are analyses that you can do of unknown compounds and get this type of information where you get we've got, you know, this percent of sodium and this percent of manganese and stuff, or whatever it is. You know, can we help identify or sometimes confirm what we think this compound is by deriving the empirical formula? Okay, so if you're given the percents of the various elements in a compound, the way that you can go about figuring out what the empirical formula is what I call the 100-gram trick. Okay, and it doesn't have to be 100 gram, but it makes your life really simple. So if you have, you know, okay, we've got 20% carbon, we've got 35% hydrogen, and whatever it ends up being is oxygen left over. Pretend you got 100 grams of it, okay? And then you know you got 20 grams of carbon. I forget the numbers that I just made up off the top of my head. 20 grams of carbon, 35 grams of hydrogen, and however many grams of oxygen. Okay, and if you know grams of those elements, you can then use the atomic weights of those, or the molar masses of those, I should say, to figure out how many moles you would have of those. Okay, and if you know the ratio of moles, you know the ratio of atoms in the empirical formula. Okay, blah blah blah. Let's put some stuff on the board here. Okay, so empirical formula. Okay. Which I will abbreviate EF. Okay. From analyses. Okay. All right. General idea. And the 100-gram trick. Trick might be overstating it, but whatever, we'll call it that. Alrighty. Okay. So, I just have a little note here of what I said. Remember when we used the formula and calced the percent by mass, okay? of each atom, I should say. Of each atom, okay? You can sort of do the reverse. Okay? All right, and I'm going to show this by jumping right on into an example. Too long. Okay. All right. So. I don't know. Yeah, I guess this is helpful. So your notes are complete. I'm always really explicit, and sometimes I worry too explicit in the things I write on here. But I want your notes to tell the whole story. Okay, so unknown sample can be analyzed. Okay, and obtain the mass percent, okay, of the elements. Okay. And can use to determine the empirical formula. Okay. All right. So our example here. Say an analysis shows a sample is 24.5% sodium, okay, 14.9% silicon, okay, and 60.6% fluorine. What is the EF, the empirical formula? Okay. All right. So I guess I'm talking about being explicit here. I have the method written out for you, the approach. So in case you have to do one of these problems, method. Pretend to have 100 grams of this mysterious unknown. Okay. Based on this, how many grams of each okay? Convert those grams to moles, okay? And what is the simplest whole number ratio of those moles okay? That is the empirical formula. Yoo-hoo. Okay. All right, so let's do all that stuff for our example here. All right. I don't think I'll do a whole lot of showing you how I convert those percents from the grams and stuff. I think you can probably see that, right? So this is going to mean that you have, if we assume this 100 grams, we are going to have 24.5 grams of sodium, okay, and 14.9 grams of silicon, okay, and then 60.6 grams of fluorine. Okay. All right, now let's convert those to moles. Okay, so moles of sodium. All right, let's just moles of silicon, moles of fluorine. Okay. Always start with what you know, the discrete value that you're given at this point. We weren't given it; we figured that part out, but you know what I mean. 24.5 grams of sodium. I'll leave out the sodium here just to make it quicker. Okay. Sometimes that's really useful. I probably shouldn't even leave it out at this point in your guys' career, but anyway. 24.5 grams. For every 1 mole of sodium, I get this, remember, from the periodic chart. The periodic chart gives me the atomic masses. It also gives me the molar masses, okay? So just reading it off the periodic chart for sodium, okay? 1 mole is 22.99 grams. Okay? Set this guy up. That's going to be 14.9 grams of silicon. Read it off the periodic chart. 1 mole of silicon is, it's right here, 28.09 grams. Okay. 60.6 grams. Okay. 1 mole. 19.00 grams. Okay. All right. Grams. It's going to spit out. All these are going to spit out the moles of the respective atoms: moles of sodium, moles of silicon, moles of fluorine. And so this guy is going to be 1.06 moles. Okay. This is 0.530 moles. Okay, running out of space, so sorry. And this is 3.19 moles. Okay. All right, so we know that that's the ratio of these atoms. So we're just about there. All right, we need the simplest whole number ratio. Okay, and you know, a lot of people can, you know, you maybe just have an intuition about how you come up with the simplest whole number ratio, or at least in the beginning the ratio. Okay, in general, what you're going to do is you're going to take the smallest one and divide it into the others. Okay. All right, and then, you know, hopefully that gives you nice, clean whole numbers. If it doesn't, then you'll be able to do what I think will probably be a fairly obvious manipulation to get the whole number ratio. All right. Okay. So, oh shucks, darn. So sorry. Okay. So our next step is to divide the smallest number into the others. That's a little vague, but given this context, you know what I mean. Okay. All right, so the smallest is the silicon. Okay, so we can figure out sort of how silicon relates to the other two. Right, so the ratio of sodium to silicon, okay, is 1.06 moles, okay, divided by 0.530 moles, okay, and that comes out to be 2, or roughly, okay. There's always in these kinds of things, those original percents that were given to us in the problem, there's always a margin of error in those. They're not perfect analyses. Okay, so this isn't exactly 2 to 1, but it's close. Okay, so it's about 2 to 1. Okay, and then the ratio of fluorine to silicon. Okay, and that is 3.19 moles, okay, by 5.30 moles, okay, and that is roughly, that is roughly about 6 to 1, okay. This is probably silly, but just for completion, okay. Ratio of silicon to silicon, it's obviously going to be 1 to 1, right? 0.530 moles, 0.530 moles is 1 to 1. Okay. All right. So therefore, these came out to be whole number ratios. Okay, your silicon is going to be 1, and your your silicon is going to be 1, your fluorine is going to be 6, and your sodium is going to be 2. So this point in the process, it immediately spit out the empirical formula. And I'll do another example where it doesn't. Okay, you got to do a little bit more manipulation. Okay, so the empirical formula is sodium 2, fluorine 6, silicon. Actually, it's never shown that way. Sorry, silicon 1, and it would be okay if you had those mixed up. Hard to explain at this point in your careers why those are like that, but the silicon would typically be in the middle of the formula. But again, it wouldn't matter if you had them switched. Okay. All right. So, as I alluded to, sometimes you don't get whole number ratios at this point in the process. Okay. So, occasionally. That gives you a cleaner ratio okay? But not whole numbers. Okay. All right. Okay, so yeah, so this example here is going to sort of speed forward, so that we don't have to do the percents again and do all that, so that we get to the novel part of this problem. So, an example from the book. From your textbook, okay, generated this molar ratio. 3.407 moles of carbon, okay, 4.54 moles of hydrogen, okay, 3.406 moles of oxygen. Okay. All right, so dividing by the smallest. Okay. Ratio carbon to oxygen is 3.407 moles, I didn't even set this up, right? Clearly it's 1 to 1. Okay, so it's about 1 to 1 carbon to oxygen. All right, and then ratio of hydrogen to oxygen is 4.454 moles. Error there. That should be 3.406, right? Just like it was there. Of oxygen, that gives you 1.33 to 1, and then the oxygen to oxygen is obviously 1 to 1. Okay. So now, what that would give you, if we were to create a formula, that's going to be C1H1.3301. Okay. And clearly, you can't have 1 1/3 hydrogens. Okay. You don't have the simplest whole number ratio. Okay. So what do? Perhaps you can see it, but multiply through. Okay. This is a little bit like what we did with balancing equations when we came up with some sort of fractional coefficient for in the middle of a balanced equation. Multiply through by the whole number that will give you the smallest whole number ratio. In this case, it's a matter of multiplying through by 3. And so take that dude, and to be honest, it's all, yeah, most of the time it's going to be, oh man, I said 3 and wrote 2. Most of the time it's going to be multiplying through by 2 or multiplying by 3. If one of these had a 0.5 in it, then that would be an indication you need to multiply through by 2. If you have something around a third, it means you got to multiply by 3. Okay, I guess 0.25 you might multiply by 4 or something like that, but it seems like most of the time it's 2's and 3's. All right, so multiply that dude by 3. That's going to give you C3 H. What does that give you? 4 O3. Okay, and so there's your empirical formula. All right. Cool, cool, cool. Let's see. Okay. Now, what if you're talking about a molecule? This is actually a molecular compound here. We know we can determine this and use this to figure out the empirical formula, but do we know that that is the molecular formula? No, we don't. If you remember from maybe the last lecture or lecture before that, that with molecular compounds, compounds that are made up only of nonmetals on that right side of the periodic chart, sometimes their empirical formulas are not the same as their molecular formulas. Okay, there's some whole number multiple of their empirical formula. Okay. Okay, so what can you do in that situation? You need a little bit more information to do anything about that. Okay, if you were after the molecular formula, okay, you get some, maybe you get some analysis data like we've been getting, percentages of the various elements or moles of the various elements. And with a molecular compound, just like we just did, you can figure out the empirical, but you're going to need a little bit more to extend it to the molecular. And the further bit of information that you might have is, what if you had the molar mass or the molecular weight of that compound? Okay, and they may seem like, oh, well, isn't that convenient? God come down and tell you what this was. This is actually also analogous to a realistic situation. There are instruments called mass spectrometers that can actually indicate what the molecular weight or the molar mass, again, it's the same thing, just different units, what those are. And so potentially you could get this information of the various percentages of your elements, and then you can also get the molecular weight of the compound all together. And then all you have to do is, if you know what the empirical formula is, you can figure out what the formula weight is of that formula, and then you compare it to the molecular weight that you're given, okay? And if they're the same, then the molecular formula is the same as the empirical formula. If they're not the same, that molecular weight is going to be some whole number multiple of the formula weight that you got by figuring out the formula weight. That makes sense? You got it? Can I move? No, I'll do a problem. Okay, let's do a problem. All right. Okay, so, but, what if a compound is molecular? Okay. Remember, empirical formula and molecular formula are not necessarily the same. Okay. All right. Okay.
molecular formula doesn't have to be the smallest whole number ratio. Okay.
Molecular formula is simply what are the various atoms that are connected together flying around all over the place.
Okay. Might be in a larger ratio than the smallest whole number ratio. Okay.
Still going to be a whole number,
But it might not be the smallest. Okay.
all right, so
Let's do an example. Search blue.
okay, so
Methyl pentanoate.
okay.
Oh.
Okay. I guess I'm trying to. Yeah. I'm just trying to show you an example. Again, I've showed you earlier in the notes where you have a compound that has a molecular weight that's not the same as its empirical weight. I'm sorry. It has a molecular formula that's not the same as its empirical formula. So methyl pentoate, the molecular formula is C6H12O2. Okay. All right. But clearly, that's not the empirical formula because that's not the smallest whole number ratio. Okay. The empirical formula is going to be C3H6O. Okay. Can't remember if I ever said that. Yeah, I must have said at some point that if you only have one atom in the formula, you don't have to put a 1. I'm sure you guys have figured that out by now. Okay, so that was just sort of establishing that they don't have to be the same. Now let's do an example of one of these analyses where we find that out for an unknown compound. Okay. So, however, can determine the molecular formula, okay, from the empirical formula if given the molecular weight. Yeah. All right, so title of this section is given percent composition. That's what we were given at the beginning of the example, right? Certain percents of sodium and silicon and fluorine. Given percent composition, and molecular weight, okay? Get the molecular formula. Molecular weight, molecular formula. Okay? I mentioned here, analytical instruments, okay, called mass spectrometers. Okay. Can give molecular weight of an unknown compound. in real in-person lectures, you can never do that, because right now people will be like, dude, I didn't stop writing that. And actually, maybe it's annoying because still you got to stop your video there and replay. But you can stop your video, replay, pause, and write down all my scribbles and stuff. When I was a brand new teacher, I was pretty bad about that. I'd write it and then I'd erase it and stuff. And I always have to tell the story of my physics teacher back in college, who he literally did this. Sorry, rambling here. Silly little story, I'll tell you. He was right-handed and he would write like this. He would go, da da da, and da 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 da, bless his heart. Okay. Anywho. Alright, so jumping into an example. Unknown powder was analyzed. Okay. And had the following composition. Okay. I'm sorry, the following percent composition. 73.7% carbon, 12.3% hydrogen, and 14.0% oxygen. Okay. Also found to have a molecular weight of 228.7. Oh no, sorry. 228.37 atomic mass units. Okay. What is the molecular formula? Okay. Okay. All right. So first thing, we'll do the 100 gram technique, or the 100 gram trick. Okay. The 100 gram trick process. Okay. And I showed you how to do that earlier. And if you did that whole process, you take, 73.7 grams carbon, 12, and again, by the way, you could use any quantity. It doesn't have to be 100 grams. You just multiply those through and stuff, except the math is, you don't even have to do any math when you make it 100 grams. It's just get rid of the percent and put a gram in there, a G. Okay, so you get those grams. You can take those grams, convert those into moles, okay? Divide by the smallest one and get the smallest whole number ratio, okay? And if you did all that stuff, what it would spit out would be C7H14O. Okay, it might be good practice. Pause the video, get some scratch paper, and do all that stuff and come up with that yourself. Okay? Okay, so now what we would want to do is figure out, well, what would be the formula weight given that empirical formula? Okay, and if the formula weight is the same as the molecular weight, then we know that is indeed the molecular formula. Okay. So based on that empirical formula, okay, generate the formula weight. Okay. All right, so you've got your carbons, you've got your hydrogens, we did this last time, you've got your oxygens. We have, for the carbons, you get your atomic weights off the periodic chart, 7 times 12.011 AMU, okay? And then we have 14 times 1.001 AMU, okay? And then we have 1 times 15.999 AMU, okay? And that is going to equal 84.077 AMU. And that 14.014 AMU, okay? And 15.999 AMU, okay? And so our sum is 114.09 AMU. Okay? Okay, so we look and see that our formula weight is not the same as our molecular weight. So our molecular formula is actually different than that. And what you're always going to find is that this is some whole number, what's the math term? Let's do it this way. This is some whole number multiple of this one, okay? And I think you could right off the bat see that it's 2, okay? And so what that must mean is that the molecular formula is twice all those, C14, H28, and O2, okay? Really put this explicitly here, don't I? Okay, so figuring out the whole number multiple. Okay, and that is going to be. There, 228.37 AMU. It doesn't have to be 2. It could be an even larger whole number multiple. Okay, you can have very large molecules sometimes. 114. Okay, I'm so sorry. That's just rude. 2, okay? Therefore, the molecular formula is 2 times C7H14O, okay? C14H28O2. Okay. All right. Oh, yeah. This is actually a fatty acid called myristic acid. Fatty acids are what make up our fats, actually. So you can take fats. Digress here. You can take fats and you can treat them with hydroxide, okay? And you'll get the, if you treat them with sodium hydroxide, you'll get the sodium salts of your fatty acids. Why am I telling you that? That's the process of how you make soaps, okay? That's essentially what soaps are. They're the sodium salt of a fatty acid, okay? If anybody remembers in a movie called Fight Club, great movie from a long time ago, they show that process. Okay, all right, so I'm going to talk now about something called combustion analysis, and I've really kind of gone back and forth on should I show you the whole nitty-gritty of this. it's something that's done in the real world a lot, but to do an example problem is very involved, and I just want to get you, I just want you guys to get the sort of big picture of how you do these things. And what combustion analysis is, it's usually hydrocarbons, okay? And so what are the products? You got it, carbon dioxide and water, okay? And what you'll often do is you can, okay, so I've got some unknown hydrocarbon, okay, and I would like to figure out the molecular formula of that, okay? So you do a combustion analysis and you can actually collect the carbon dioxide and the water, okay? And you can get masses of them, okay? What mass of carbon dioxide you get and what mass of, sometimes it's indirectly, rather, you don't grab the carbon dioxide, solidify it and put it on the scale, but the instrument can do it indirectly. And so one way or another, you get the mass of carbon dioxide generated, you get the mass of water generated, okay? And so now how are you going to, you're not getting the mass of individual atoms, all right? So this is a trickier problem here. But the thing is that given the mass of carbon dioxide, okay, what you can do is you can go, okay, I get that mass of carbon dioxide, well how many moles of carbon dioxide is that? I just do that with the molar mass. Okay? Once I know the number of moles of carbon dioxide, okay, I know the number of moles of carbon that was in my original sample, because that's where the carbon came from in a combustion reaction. When you take some hydrocarbon, all the carbons that end up in your carbon dioxide came from that sample there. Okay? Same with the hydrogens. You take the water, okay, so I've got X grams of water, I figure out how many moles of water that is, okay? And for every mole of water that was created, I actually got, I had double that many. Why double? Because it's H2O. I had double that number of moles of hydrogen in the original sample. And so now I figured out the moles of carbon in the original sample. I figured out the moles of hydrogen in the original sample. The only thing I don't know about is if it's a hydrocarbon with oxygen, I don't know what moles of oxygen were in the original sample, okay? And so, something I should have mentioned, you know how much you put in the beginning. Maybe you, in this example here, we're going to put in 0.2 grams, okay? You get your weight of these guys, you figure out the moles, and then you can see is there any mass here that isn't accounted for in the moles of carbon and the moles of hydrogen. That must have been moles of oxygen, okay? I don't know if this is one of those times where I explain something off the cuff and it's helpful or not, but in any case, I'm going to show you how the whole setup happens. I'm not going to go through the gory details of solving one of these problems, but I want you to be aware of it. There's a nice example in your textbook that you can follow along, okay? And again, combustion analysis is definitely a common procedure that's conducted, and so, you know, it's something that you should be aware of. All right. Let's see. Oops, sorry. Combustion analysis. All right. Okay. Sometimes don't conveniently, no, I cannot spell, I can barely spell Gideon. Sometimes you do not conveniently get mass percent of each atom. Okay. Okay. Combustion and yeah, I don't know.
good transition here, transition sentence. Combustion analysis is such a situation. Combustion analysis also usually done with hydrocarbons. You could do fancier ones that aren't just hydrocarbons, but we definitely won't get into that. Let's just try to understand the process of doing combustion analysis with hydrocarbons. Okay, so I'm going to give you just an outline of the general process. Okay. You weigh out a compound. So you've got some unknown compound. You weigh it out, 200 milligrams, or whatever the heck it is. Weigh out compound and burn in O2. Okay. The carbon of your original compound turns into carbon dioxide. Okay. And the hydrogen of your original sample turns into water. Okay. Some of these oxygens in your products, your carbon dioxide, your water, may have come from your original hydrocarbon. It wouldn't be a hydrocarbon, it would be an oxygen derivative of hydrocarbon, right? It'd be a CHO type formula. Okay. Some of these oxygens may come from it, but does make it a little bit complicated in the case of oxygen that some of the oxygens in these products also come from the oxygen in the air, which isn't something you weighed in the beginning. Okay. All right. And then you, what's the best way to say it? Collect. The process gives you the mass of CO2 and water. Okay. Sorry. Let's have a continuation. Process gives you the mass of those. You can convert those to moles of CO2 and water. Okay, molar mass of carbon dioxide, molar mass of water. Okay. The number of moles of CO2 generated, okay, it's just getting so pretty. Sorry, it's a little late, I'm getting a little punchy, equals the number of moles in the original sample. Is that the way I said? That's what I meant to say. Number of moles of carbon in original sample. All right. And same for H2O generated. It's the number of moles of H in the original sample. Okay. If you know the number of moles of carbon in the original sample and the number of moles of hydrogen in the original sample, you can figure out the mass in the original sample. Okay. By using the atomic weight. I'm sorry, the molar mass. Okay, so now you calculate the mass of CO2
H in the original sample, okay, based on this, okay? Remember that you weighed out a certain amount. You can add up these two masses and see if there's any amount left over, okay? You weigh, if you, calculated the number of grams of these in your original sample and it came out to be what you put on the balance in the first place, then you know that there was no oxygen that was part of your original sample, okay? But if this mass sum is less than that, you know that the leftover stuff was oxygen from the original sample, okay? By conservation of mass, okay? We'll put it on the balance, it's got to come someplace. Okay, and so any mass left over, okay, is a third element, okay, usually oxygen. Okay, like I said, you can do fancier ones that where it's not limited to oxygen, but for the most part and for the scope of our discussion, oxygen. Okay. Now you can get the mass of oxygen in original sample. Okay, get the mass of oxygen in the original sample by subtraction. Okay, figured out how much mass was left over, or how much mass from the carbon and hydrogen, subtracted from that leftover mass is oxygen. Once you know that mass of oxygen in the original sample, you can figure out the moles of oxygen in the original sample. And then convert to the moles. Oxygen. Now, should be a big O. And then, through this long tail, you may not realize it, but you're home free. Now you have the moles of carbon, the moles of hydrogen, and the moles of oxygen. Okay, so you've got the simplest ratio. Now you just need to decide if it's the simplest whole number ratio. Okay. Right, and then so you get the moles, ratio, and then you could even go so far as to, I also got the molecular weight from using a mass spectrometer, do the thing that we did in the last one where you decide is the empirical formula the same as the molecular formula, okay? Long process, not going to do the example. I think I used to do the example and it just, the eyes start spinning in people's eye sockets, okay? So, especially in summer, because this stuff is coming fast, okay? Stay positive, stay caffeinated, that's what I do. And, just try to always pat yourself on the back for how much you've accomplished. Let's see, you guys are going to see this. I just have to do that. When the heck are you guys going to see this? You guys are going to see this next Wednesday. By next Wednesday, be like 30% of
30% of the way done with the class. Okay, that's amazing that you've, so I know you're huffing and puffing, hang in there, and we're going to get to the end. Okay. Next thing I wanted to go over is kind of some features of the balanced chemical equation. Have we really used those features? I haven't really used these features yet. The balanced chemical equation can give you a lot of information. Okay, those coefficients, can tell you, well, if I got 1 mole of that reagent, I need 3 moles of that reagent, okay? And if I've got those, I can potentially make 5 moles of that, okay? And you can extend that even farther. So you know that molar ratio, okay, these 2 ingredients. Well, I know how much mass of this guy. How much mass of this guy do I need? Well, I'm going to take the mass of this guy, okay? And I'll figure out how many moles is that, okay? I'll then use these coefficients, because the coefficients in the balanced chemical equation tell me, in the simplest way of thinking about it, it tells you the number of molecules, or the number of compound, units. Molecules is always easier to talk about. The number of molecules of these things that you need that react together to make the number of moles, but it also tells you the number of moles that react together, right? Yeah, okay. No more analogies, can you? So you can do a lot of stuff like that, and that's going to be useful and important to be good at that kind of stuff. So let me show you some examples of doing those types of manipulations. Okay, so. Quantitative information from balanced equations. Quantitative info from balanced equations. Okay. All right, so this is just our general part of this, general info in this section. Sorry, let me double check something here. Okay. I had this horrible fear, like, did I press the record button? That would be so depressing. I did. Okay. All right, general. Okay, so here's some random example. What are we doing? We are burning glucose. It happens in your cells. It gives you energy, it keeps your body moving, so forth and so on. Critical process to our survival. Okay, so general, let's say you have glucose. So glucose, the formula of glucose is C6H12O6. Okay. Glucose is a sugar. Sugars always have a lot of oxygens on them. Plus 6, 2, okay, goes to 6 carbon dioxide plus 6 water. Okay, that's the balanced chemical equation there. Okay. Yeah. I was like, wait, yes, that's definitely the balanced chemical equation. Okay, and this is glucose, often abbreviated GLU. Okay, all right. And so, really making your notes explicit here. According to that formula, for every 1 molecule of glue, okay, you need 6 molecules of oxygen, okay? But the balanced chemical equation, BCE, describes the molar ratio as well. Okay? So, for every 1 mole of glue, need 6 of O2. Okay? All right. Here's a little question for you to ponder. Don't ponder long. For every 6 moles of oxygen, how many moles of water do we create? Okay. And that would be 6. For every 6 moles of oxygen you use, you create 6 moles of water. Okay. And lots of ways you can describe this. In order to create 12 moles of carbon dioxide, you need 2 moles of glucose. Okay? Because that ratio is 6 to 1. Okay? So this gives you the ratio of the reaction. Okay? Reagents to reagents, reagents to products, products to products, so forth and so on. All right? Okay. Not too crazy hard, right? Okay. A little bit left. Why am I saying this? Yeah, okay. Say you have 3.4 moles of glue. Okay. I guess this is just a reminder. How do we convert that to mass of glue? Okay. And the answer is the molar mass of glucose. Okay. All right. If we knew we were burning 3.4, and I'm not talking about metabolism like humans burning. Let's say we're doing it in a lab. Okay, if we're burning 3.4 moles of glucose, of glue, we could do the following, okay? We could calculate, okay, we know we're burning 3.4 moles of glue. We could calculate theoretically how many, what do I want to know? How many moles of carbon dioxide will we create, okay? You know, so the same kind of process that we were doing over here, except now this isn't such a convenient number, okay, but this still gives us the ratio, so using those ratios we can take that and convert it into moles of carbon dioxide, okay, so you can calculate the theoretical okay, number moles carbon dioxide created. Okay, or water. All right. By the way, the reason I say theoretical is a lot of the time reactions they don't do 100% what they're supposed to do. Okay. Sometimes you get side products and it makes something else. Okay. I mean, you know, if burning all hydrocarbons only created carbon dioxide and water, we wouldn't get ashes at the end, right? Okay. The majority of it is actually turned into carbon dioxide and water, but there are side reactions, side products, and stuff like that. So that's why I say theoretical. Okay. You might not get, you know, exactly what this is going to predict you get, but theoretically, if everything went perfect, every molecule did what you anticipated it to do, what is the theoretical number of moles of carbon dioxide created? Okay. Or you could calculate the moles of O2 required. Okay. Right, so you know that you're burning 3.4, how much oxygen we're going to need, how many moles of oxygen are we going to need. You can use that ratio there, okay? You could also, or calculate the mass of oxygen needed. Okay? And these are the kinds of things that we will often do with those balanced chemical equations. Okay? All right, and I do have a note here, put it in your notes. We say theoretical because sometimes reactions do unexpected things, create side products, byproducts, stuff like that. And this gets into a concept that we're going to look at in terms of yield. Okay? There's theoretically how much you can generate with this process. How much do you actually generate with the process? We'll talk a lot in terms of, or chemists will talk a lot in terms of percent yield. Okay, so theoretically we're supposed to do this. You know, it's supposed to give you 10 grams of product. It only gave you 8 grams. It's 80% yield for that reaction. Okay. All right. Okay. I've got a sort of fancy, sciencey, overcomplicated word way of explaining that, oh shucks, I got rid of the formula. Those ratios, we can actually turn those into multiplying factors in dimensional analysis. Okay, so in the last one it was for every 1 of glucose you got 6 carbon dioxides. We're going to be able to do this for every 1 of glue. you get 6 carbon dioxide, okay? We're going to be able to use that as a factor in dimensional analysis if we need to, or we could do the reverse, okay? We could have 6 carbon dioxides over 1 glue, okay? This is one of these things that I've been doing it so long I can't decide if that's kind of, I don't want to say mind-blowing, but if that's kind of like, wait, why can you do that? You know, that's no more crazy than, there are 2.4 centimeters in an inch. Is that what we decided that Gideon failed to put on the quiz? 2.4 centimeters in an inch. And so you can make one of those multiplying factors with 2.4 on the top and an inch on the bottom type thing. Okay? All right. But like I said, I've got some fancy sciencey pronounced way of stating that. And that is the coefficients of a balanced chemical equation, BCE, okay, are stoichiometrically equivalent quantities. Okay. I think I even made up this awkward phrase because it's useful. Yes. Okay, so for example, what I mean by that, their equivalencies, is that C6, H12O6, in the context of that reaction, 1 of glue is equivalent to 6O2, which is equivalent, again, you know, oxygen ain't the same as glucose. Yeah, I know that's weird. But in terms of stoichiometric equivalencies, in the context of the reaction we're talking about, they're equivalent, okay? Equals 6 carbon dioxides, which equals 6 waters, okay? And I do all that so that these, you know, if those equal each other, I can divide both sides by that, and it'll equal 1, and thus, that means I can multiply anything in the world by this over that, and not change it. It's all just sort of a justification for I can create those dimensional analysis factors. Therefore, can create a ratio fraction okay, of any two and multiply something by that fraction without changing it. This, I think, is a place where my first off-the-cuff explanation is more useful than that. Okay, so some examples. Let me show you what. Show you some neat things we can do with that. Okay, so some examples. Okay. Oh, we're still using that same equation. Right on, right on. To burn 3.2 grams of glue, okay, O2 do we need? Okay, maybe without this discussion that we just had, this would seem like daunting, like, oh, how are we going to figure that out? And I note here that you can do it in sort of one long dimensional analysis, or sometimes, you know, maybe if you're just starting out and getting comfortable with some of these manipulations, it's easier to do it in a couple smaller, simpler dimensional analyses. Okay, what am I going to show you? I'm going to show you some smaller, simpler ones. Okay. And then I'll show you one, and then I'll do another example where I show you use a long, hairy one. Okay. Okay, so told us the mass of glucose. So let's figure out the moles of glucose. How did the problem state it? Yeah, so we want to burn 3.2 grams of glucose. Let's figure out how many moles of glucose that is. We'll use the balanced chemical equation to figure out, given that number of moles, how many moles of oxygen do we need? Given that number of moles of oxygen, how much mass of oxygen is that? Okay. All right. So moles of glue, okay, is 3.21 of glue. Okay. 180.16 grams of glue. Okay. For every 1 mole of glue. That's just the molar mass of glue. Okay. Oh, got my gram. Take a point off Gideon's test. Grams of glue. Grams of glue. Okay. Is 1.78 times 10 to the negative 2 moles of glue. Okay. All right. Well, now based on that, how many moles of oxygen do we need? Moles of O2. Okay. Well, start with our discrete value that we're given, given by ourselves, is 1.78 times 10 to the negative 2 moles of glue. Okay. We already know this, but I always like to make these things explicit. For every 1 mole of glue, okay, we need 6 moles of O2. That's just a coefficient ratio for the balanced chemical equation. Okay. And so at this point, you know, with these two multiplied by each other, we have the number of moles of oxygen. So, not going any farther. We're keeping it simple. Okay. So, moles of glue. That is going to give us 10.6 times 10 to the negative 2 moles of glue. Okay. And then to get our mass of oxygen, okay, simply take the moles. Darn it! Sorry. Moles of oxygen. Okay. So to get our mass of oxygen, simply take our moles of oxygen, use the molar mass of oxygen to get the mass. Okay, so 10.6 times 10 to the negative 2 moles of O2. Okay, 1 mole of O2 is 32.00 grams of O2. Moles of O2, gonna spit out 3.42 grams of O2. Okay? Okay, let me do another one of these, and rather than kind of that really stepwise process, I'll show you how you can do it in one long dimensional analysis. And hopefully you've been learning to love dimensional analysis like I love dimensional analysis. I do, it's sad. Blue. Okay, so say in a different reaction, you produce 5.34 grams of CO2, okay? How many grams of glue did that take? Okay. All right, so how do we start this? Well, let's put over here in our calculation title, which please adopt. Let's put, what are we after? What do we want? There's a lot of mumbo jumbo in all these problems, and sometimes there's really sort of, you could say they're purposeful distractions in the problems, okay? But what I think they're trying to do in these problems is they're trying to reflect reality, you know? Reality has distracting bits of it when you're trying to solve a problem, but you have to sort of peer through there, not get distracted by the stuff, and figure out what do you want. All right, what do we want? We want mass of glue, okay? So we'll put that here, mass of glue, okay? Start with a discrete thing that you're given. Given 5.34 grams of carbon dioxide. All right, so 5.34 grams of CO2. Oh, what do I multiply next by? You know, I mean, sometimes you can come up, first of all, these dimensional analyses that we generate, there isn't only one correct one, okay? There's multiple ways you can set them up. Sometimes if you're not exactly sure what to use next in your dimensional analysis, you can think about, well, I know my answer I'm trying to get isn't supposed to have grams of carbon dioxide, so how do I get rid of this unit? Okay. Well, one way I can get rid of that unit is by using the molar mass of carbon dioxide. Okay. So by that I mean, for every, I need to make this smaller. I don't know why I'm writing so huge all of a sudden. Okay, maybe a little shrinking down here. Okay. Sorry for font change in the middle of a dimensional analysis. All right. For every 1 mole of CO2, okay, how many grams? Well, you get the molecular weight, you can do that in a separate problem. Sometimes in problems like this, I might even give you the, not molecular weight, molar mass, Might even give you the molar mass so that you don't have to, okay, 1 carbon, 2 oxygens, what's the molar mass? I'll tell you right now what it is 44.010 grams of carbon dioxide, okay? Grams of carbon dioxide, and cancel out. At this point in the calculation, we have moles of CO2. Ooh, now we're getting someplace. Well, the balanced chemical equation gives us that ratio of moles of CO2 to moles of glue, okay? And it is if we look back at that balanced chemical equation, 1 mole of glue, okay, generates 6 moles of CO2, okay? Moles of CO2, moles of CO2. All right. At this point in the calculation now, we have moles of glue. Oh, snap, we're almost there. Okay, we need mass of glue. We got moles of glue if we're at this point. All we got to do is use the molar mass of glucose, okay, and we're home free. And then punch all that stuff into our calculator. Okay, so 1 mole of glue, okay, is 180.16 grams of glue, okay, and that's going to give you 3.64 grams of glue. Okay, pretty handy, right? Saves a lot of stuff if you can do it like this. If this throws you off, you know, when you're in test or whatever the situation, even homework, you know, go ahead and do it out step by step by step. You know, don't take this as some challenge that you necessarily need to do. But once you get comfortable with dimensional analysis, it's pretty nice and convenient. Yeah. Okay. Now I'm going to look at something, kind of double back to something that we talked about a little bit when we were discussing theoretical yield. Okay. You know, if we, yeah, where do I start? If we know, you know, wait, is that what we just did basically? Ding dong? Is that what you did? No, that's too good. We should have done it that way. You can actually look at the last one, at the last problem we just did to help us understand theoretical yield, okay? Theoretical yield, I mean, I already talked about it earlier, so you might sort of understand it, but theoretical yield is, you know, if the reaction goes perfectly, given this amount of starting material, okay, if every molecule does what it's supposed to do, what mass of product can I get, okay? So you could actually, we can look at this last example and reverse that, actually. If you start with 3.64 grams of glucose, what is the theoretical yield of carbon dioxide? Well, every single molecule, this dimensional analysis, every single molecule is being converted. So starting with 3.64 grams of glucose, the theoretical yield of carbon dioxide is 5.34 grams of carbon dioxide. Okay, that's the theoretical yield. And so that's an important concept we're looking at. We're going to look at that. We're also going to look at, you know, you'll do calculations like that, and you already know how to do that, figure out the theoretical yield. Okay? And then in the problem you might be given, well, the reaction was run. That reaction that we talked about on glucose was run on the 3.64 grams of glucose, and we only generated 4.2 grams of carbon dioxide. What's the percent yield? No big stretch. You take the 4.2, put it over to 5.34. That was the theoretical yield. Multiply that. That's percent yield. Easy. Okay. So this next section, not too bad. The one maybe tricky part of this is in a lot of reactions, say we were setting this up and, we know that the ingredients we need are glucose and we need oxygen. A lot of the time we won't do a reaction like that where, okay, let's figure out exactly how much oxygen do we need for that 3.64, okay? Or if it was reversed, how much glucose do we need for that? We often use one of the reagents in excess, more than you need, as dictated by the balanced chemical equation, okay? What we're going to be sort of tasked with here is figuring out which is the limiting reagent, okay? So you have one, let's say there's two reagents. You have one reagent that you've used in excess, you've used more than you need. Then the other one is the limiting reagent. And the example I give here in my notes, cheesy example coming, is if you're making hot dogs, all right, and you've got 7 buns and you've got 5 dogs, okay, then what is your theoretical yield of hot dogs? It's 5 hot dogs, okay? I don't care that you got 7 buns, you only got 5 dogs, you can't make any more than 5 hot dogs. And what is your limiting reagent? Dogs, okay? Because you've got an excess of buns. That's it, okay? Just sometimes, it's not hot dogs and buns, it's moles. Okay, so you might find out, oh, I got that many grams of glucose and I got that many grams of oxygen. Which one of those is the limiting reagent? Okay, well, I got to convert it to moles. Okay, convert that to moles, use the balanced chemical equation and decide, we've got some approaches to that, decide which one of those is in excess. Okay, and that's about it. And that, I think, takes us to the end of the chapter. Woohoo! Alrighty. I'm bored of these colors. I being 1/8 Irish, switch to green. Okay, so we're now on Roman numeral 8. Okay. Call this action a reaction. Can only go as far as the limiting reagent. Okay. And the theoretical yield can only go as far as your limiting reagent. 5 hot dogs, that's your theoretical yield. That is your theoretical yield. You could drop a dog and you only get 4 hot dogs, but our theoretical yield was 5 hot dogs. Okay, so I'll put in, I got in parentheses here in my notes. Same for theoretical yield. Okay. Theoretical yield is only as big as the limiting reagent will allow it to be. All right, and here's the hot dog example in text. A hot dogs, limiting reagent. And completely over-explaining this hot dog thing now, but it'll be helpful if you look back at your notes in a month or something. All right, so 1 dog plus 1 bun gives you 1 hot dog. Okay, pretty simple stoichiometry. These are vocab words. Okay. That's exactly nothing. No good variety here. This is exactly what I just verbalized. Say you have 5 hot dogs. Okay. And 7 bonds. All right. What is the max hot dogs you can make? Okay. In this situation, dogs are the limiting reagent. Okay. Okay. I'll start this up here. Okay. Reactions and limiting reagent. Getting back to chemistry. Okay. Limiting reagents. Reactions often have limiting reagents. Okay. Don't always have to. Sometimes, in the laboratory, we actually try to do the exact, quantity that you need of all the reagents. Sometimes there's only one starting material, okay, like in a decomposition reaction, right? I have here, remember that the balanced chemical equation, BCE, gives you the ratio of reagents needed. Come on. Or the ratio needed of reagents. Okay. Difficult to provide exact quantities needed. Therefore, reactions often have an excess of one or more reagents. Okay. Okay. If your reagents are 1-to-1, then it's pretty easy to decide which one of them is limiting. Okay. You simply, if you're given masses, you simply figure out the moles, you decide which one's smaller, and that's the limiting reagent. Okay. If the balanced chemical equation says that they're, it's 1-to-1. Okay. But if the balanced chemical equation says your ingredients, you need 6 of this and 1 of that, you can't just look at the number of moles. You got to take into account that 6-to-1 ratio. Okay. All right. So. Simplest reaction to evaluate for a limiting reagent. Okay. Is 1-to-1 reagent reactions. That's not the world's smoothest sentence, but oh well. Example of that, you take carbon solid, you can burn it with oxygen and get carbon dioxide, or oxidize it, okay? Gas, right? And if you're doing this reaction, if started with 2.3 moles of carbon solid and 4.1 moles of oxygen, okay, gas, what's the limiting reagent? Okay, clearly it's the carbon, okay? So carbon is limiting reagent, okay? Here's a question for you based on this simple reaction. Just to backtrack, a little practice here. What's the theoretical moles of CO2 you can create? Okay. And once you've established which one of these is the limiting reagent, okay, we know that the carbon is the limiting reagent. In terms of figuring out the theoretical yield, you ignore the other one. We got that in excess. This is the one, and that's the limiting reagent that limits the theoretical yield of carbon dioxide. Okay. This is often referred to as the theoretical yield. Okay. Theoretical yield is often expressed as mass. Okay. Often we don't. Sometimes you do, but most commonly, when you're talking about the theoretical yield of a reaction, you're talking about the mass. So theoretical yield, Ty, usually in mass. Okay. All right. So that's no problem about deciding which is the limiting reagent for a 1-to-1 type reagent situation, but what if they're not? Okay, let's look at an example like that. Okay, so, oops. Getting crazy with colors here now. Let's go back to black. All right. Non 1-to-1 reagent reactions, okay, they are going to require a little more math. Okay. 2 aluminums, okay, plus 3 chlorines. Okay, it's going to give you 2 aluminum chlorides. Okay, not 1-to-1. Alright. Say you have 2.3 moles of aluminum. Okay. And 3.1 moles of chlorine. Okay. Which is the limiting reagent? Okay. And what is the theoretical yield? Once you figure that out, what's the theoretical yield of aluminum chloride? Okay. So the way I approach this is do two separate calculations. Okay. Take each one of these and say, well, given 2.3 moles of aluminum, how much chlorine would I need? Okay? And then I go, well, okay, given 3.1 moles of chlorine, how much aluminum would I need? Okay? And one of those will generate more than you got. Okay? And if it generates more than you got, you know that it itself is the limiting reagent. You don't have enough to do all of it. Okay? I'm sorry. Darn. You'll see it. It'll be very clear when I do it here. But if you take one of these, you multiply it, and it generates a number, and it says it's more than what you have, okay, of that other reagent, then the other reagent is the one that's the limiting reagent. Sorry. Okay. Okay, I got a nice simple way here actually to say it. Go to green. Sort of the general approach. Okay. For each reagent, use dimensional analysis, DA, to decide how much need of the other reagent. Okay? Maybe this isn't the greatest way to say it. We'll see. Only one of those calculations, only one calculation will generate a quantity that's available. Okay. Yeah, and that is a nice way to say it, although maybe a little complex. Only one calculation will, this is a W, sorry, will generate a quantity that's available, and the reagent that sort of initiated that calculation is the limiting reagent. Okay. Definitely much easier to see it as an example. Okay. Oh, yeah, right, I have it. And right there. So, let's see how we do it. Alright, so, start our title here, moles of chlorine needed. Okay. Given 2.3 moles of aluminum. Alright. 2.3 moles of aluminum. Okay. For every 3 moles of chlorine, you need 2 moles of aluminum. Okay. That's going to give you 3.4 moles of chlorine, sorry. Okay. You can almost get away with only doing one, I guess, particularly if that one generates what the limiting yield is, okay? And you've already figured out that the chlorine is the limiting reagent because we don't have enough chlorine in the given circumstances to react all the aluminum. So that's limiting and that's excess, okay? Still, for completeness sakes, probably good to do the other one. All right, so aluminum needed given 3.1 moles chlorine. Okay, 3.1. This should generate a quantity of aluminum that we do have available. 3.1 moles of chlorine. Okay. 2 moles of aluminum for 3 moles of chlorine. Okay. That's going to give us 2.1 moles of aluminum. Okay, and we do have that amount available. Okay, so chlorine is our limiting reagent, or I should say, better put, we have more than enough aluminum to do that. Okay, I got 2.3, we only need 2.1. This is the reagent in excess. Okay, and again, the limiting reagent is the one that is going to dictate your theoretical yield. Okay, you can only make 5 hot dogs. Okay, based on the 5 dogs. Okay. Yeah, I said it all. So, chlorine is limiting, aluminum is in excess. Symbol for excess. Okay. All right. Theoretical yield calculations. Okay, that's not going to be too hard. Once we figure out what the limiting reagent is, we can do one of these dimensional analysis to figure out what mass of product we could potentially make. We'll start with the moles of limiting reagent, or the mass of limiting reagent, convert it to the moles of limiting reagent. Once we know the moles of limiting reagent, we can use the balanced chemical equation to come up with the moles of product. So you know the moles of product, we can come up with, use molar mass of product and come up with the mass of product. Okay. All right. fermenting reagent, okay? Calc. What's the max of aluminum chloride? So I'm keeping this specific to that example. Aluminum chloride could make. Okay. That's theoretical yield. But notice, to figure out theoretical yield, I first had to be sure of what the limiting reagent was. Okay? How'd you know that? And I'm actually going to do it for this problem above. So the theoretical moles of aluminum chloride, okay, that is limiting reagents chlorine, 3.1 moles of chlorine. Okay. For every 3 moles of chlorine, okay, we generate 2 moles of aluminum chloride. Okay, and that'll come out to 2.1 moles aluminum chloride. Sure, units cancel, and we know we did the problem right. They do. Okie dokie. Alright. I already mentioned the very last thing we're going to talk about, and that, I mean, I've taken you, or we've got 95% of the way there. We just need to do percent yield, which is, say you had an example like this, and they actually told you, well, at the end you got, X amount. What's the percent yield? First you figure out the limiting reagent, then you figure out the theoretical yield, then you take the amount that you did get, divided by the theoretical yield, multiply by 100, and go home. Okay. By the way, for those of you who are going to go on and take organic chemistry, I hope you do. I generally teach the labs of that class. You will have to do a lot of these theoretical yield or percent yield calculations. Not terribly hard. I don't think this is calculus. But people do seem to forget it sometimes by the time they make their way to organic chemistry. So you might just really try to put a lockdown on this. Not one of the major things that you, it's not like, oh man, if I fumble that when I get to organic chemistry, I won't become a doctor. No, you can still get an A in organic chemistry if you fumble that a bunch. But it is nice not to have to relearn it once you get there. Okay. All right. I bring up that doctor thing I should bring. Students sometimes get a little bit too worked up and oh gosh, if I don't get an A in this class and that class, I really want to be a doctor, or whatever the case it is, whatever it is you want to be. And it's important to get good grades, particularly you want to go to something really competitive like med school. It's important to get good grades, but work as hard as you can, do as best you can, try to get that GPA as high as you can. But there are doctors out there right now that are, operating on people, and they got a C in organic chemistry. So it's not the kiss of death. Just don't want a lot. And I think I told you I failed music appreciation. Well, look at me now. Okay, sorry, getting punchy. percent yield. Okay. We have established how to calculate theoretical yield. Okay. Lots of reactions. To achieve that, okay, percent yield okay, is actual yield, the mass of product that you isolate at the end over theoretical. Times 100, and that's it. Okay, let's do an example, and then we're done. Chapter 3. Blue. Okay. Hydrogen sulfide is an impurity, natural gas, okay, that must be removed. This is a great example of what I was talking about earlier, where you get problems with a whole bunch of distractions and fluff and stuff. You know, that can remove natural gas. I don't know what the formula is for that, or you know, hang tight, sort of wade through all that fluff and figure out, okay, what do you want to know? One common removal method is the Klaus process. Almost getting to like the stuff that's actually meaningful. This is maybe interesting, but not meaningful for solving problems. Which relies on the following process. Okay. Eight hydrogen sulfides, okay, gas, plus 4 O2s, okay, all right, goes to sulfur, okay, solid, plus 8 H2O gas molecules, okay. All right. So calculate theoretical yield of S8
If, this is a cyclic sulfur molecule, actually. Not all sulfur exists that way, but a lot of sulfur does. That's a common form of elementally pure sulfur. And that may seem weird. What do you mean? There's different types and stuff? You already know that. Carbon. There's graphite and there's diamond. Okay. Just two different forms that the atoms come together and exist in. Okay. Sulfur, if 30.0 grams of hydrogen sulfide and 50 grams of oxygen were reacted. Okay. Also, calculate the percent yield if 19.6 grams of sulfur was isolated at the end. Okay. 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 Why don't you, if you're still writing that stuff down, I know some of you are actually writing down all these notes. I think that's great. I know it probably takes a lot of discipline to do that. These videos are long. But I really do think you're forming synapses when you do that. But you pause, because I'm going to erase this stuff. And I'm just going to keep up the balanced chemical equation. And I'm going to do everything above it, actually. These dimensional analysis are a little bit long, so I need kind of the whole width of the board. Okay. All right. Okay. Oh, and given in the problem, the molar masses, okay? So we have hydrogen sulfide, and this is molar masses in grams per mole, that's the unit, okay? Sorry, that's grams per mole. Handwriting's going. You're thinking, oh, the handwriting used to be good? Okay. Sorry. Oh, okay. Molar masses and then sulfur 8. Okay. Well, molar mass of hydrogen sulfide, that is, again, you can figure these things out with the periodic chart and stuff, but given all that else you can do in a problem like this, I would give you these molar masses. Molar mass of hydrogen sulfide is 34.1 grams per mole. Oxygen is 32.00. And hydrogen and I forget the name of that. I should double check that. Sorry. Sulfur 8 is 256.48. Okay. All right. Okay, so we first got to figure out this is not a one-to-one reaction, and in the problem we were actually given masses. Okay, so we need to figure out which is the limiting reagent. So we'll start with each reagent and figure out how much we need of the other. Okay, so, grams of O2 needed. Okay. Given 30.0 grams of hydrogen sulfide. Okay. All right. 30.0 grams of hydrogen sulfide. Okay. 1 mole of hydrogen sulfide. Okay. It's 34.1 grams of hydrogen sulfide. Okay. According to the balanced chemical equation, okay, for every 8 moles of hydrogen sulfide, we need 4 moles of oxygen. Okay. Nope, I should be doing this along the way. That's a good way to go. Grams of hydrogen sulfide, grams of hydrogen sulfide. So at this point, we're at moles of hydrogen sulfide. Oh, I should have said moles in here. Sorry, folks. Moles. Okay. Moles of hydrogen sulfide, moles of hydrogen sulfide. So at this point in the calculation, we're at moles of oxygen. Okay. All we got to do is multiply by the molar mass of oxygen, and we'll figure out what mass of oxygen we need. So 1 mole of oxygen is 32.00 grams of oxygen. That's a gram. Okay. Mole oxygen, and that's going to equal 14.1 grams of oxygen. Whew. Okay. Do we have that much in the reaction? We have 50 grams of oxygen, so we have plenty of oxygen. You already have an indication that hydrogen sulfide is our limiting reagent. Okay. That's often the case, by the way, with oxygen, because we often do it in the air, and there's an excess of oxygen in the air. Okay. But it's prudent to double check. Okay, so grams of hydrogen sulfide needed. Okay. Given 0 grams of oxygen. Okay. Uh, 50 grams of O2. Okay. Or 1 mole of O2 is 32.0 grams of O2. Okay. So now in the calculation, we are at, so that's grams of O2, we're at moles of O2. Well, for every 4 moles of O2, again, 8 moles of hydrogen sulfide. Okay. Moles of O2, moles of O2. So now we're at moles of hydrogen sulfide. All we need to do now is take the molecular weight of hydrogen sulfide. For 1 mole hydrogen sulfide, okay, it's 34.1 grams of hydrogen sulfide. Okay. And that gives us 107 grams of hydrogen sulfide. Okay. Don't have near that amount. We have 30, right?
So definitely hydrogen sulfide is our limiting reagent. Okay, so we can now figure out our theoretical yield of sulfur. Okay, oh, I should put a little thing in there. Therefore, hydrogen sulfide is limiting reagent. Okay. Theoretical yield of sulfur. Nice little trick you could do on your calculator is, that up here within that dimensional analysis, you figured out the moles of hydrogen sulfide. It was actually right here. So you could just sort of repeat that part. Yeah, let's don't do that. Bad advice. Be careful. To take shortcuts and they can bite you. All right, so theoretical yield. So start with the discrete amount. We have 30 grams of hydrogen sulfide. Okay. Let's convert that to moles of hydrogen sulfide. 1 mole of hydrogen sulfide is 34.1 grams of hydrogen sulfide. Okay. You produce, according to the balanced chemical equation, 1 mole of sulfur for every 8 moles of hydrogen sulfide. Okay, crossing. So grams of hydrogen sulfide, grams of hydrogen sulfide. At this point, you're at moles of hydrogen sulfide. At this point, you're at moles of sulfur. Okay, simply using the molar mass of sulfur will get you the theoretical yield in grams. Okay, 1 mole of sulfur is 256.48 grams of sulfur. Okay, 28.2 grams of sulfur is your theoretical yield. Outstanding. And finally, take it all home, our percent yield is what we actually got. It was listed somewhere in the problem. That's, what was that, 19.6 grams. Not hydrogen sulfide, that was sulfur. Divided by the 28.2. Okay, times 100 is 70%. Okay. When you do organic research stuff, you always really want something past 50%. A lot of our reactions that we do are successive reactions. So we create this, and then we use that as a starting material for the next reaction. And you do it for the next reaction. And I've done, I did 20 synthesis, 20 steps. Well, the yields are what's the right way to say that? Multiplicative? I think that's the right way to say it. I'm a little tired. But they multiply by each other. So if you have 2 successive reactions that are 50% yield, your overall percent yield is 50% of 50%, 25%. Okay? So it's important to have high yields. It's a very important concept in all of chemistry for just that reason. Okay? That's it. That's chapter 3. Nice job, guys. See you later.